Hello, Professor.
Hello, Sarah. Hello, Peyman. Hello, Meade. Hello, Mara. Thank you for connecting. Please confirm if you hear us. Do you?
Can you hear us?
Yes. Okay. And here are the in-person visitors. Okay, isn't this? You rarely see Stephen without your cat Roxy. I allowed to bring her. Okay, thank you very much for preparing slides. Just I can disable sound here. Okay, it should be less background. So the goal of our meetings that we do get skills sufficient to predict the dynamics of electronic states due to motion of nuclei. In the variety of research projects that you are already pursuing, this skill may be main and correct and directly connected to a project. It may be just something a little on the side of what you're doing, but it is the best subject that could be of common interest to all of us. So as we are going through presentations, or maybe at the end of presentations, I'll share the list of subjects to volunteer for next time. And today we are covering basic skills which are not yet a part of electron dynamics, but they are some additional things which increase your functionality and that will help you to progress in the rest of our activities. So let me share a screen and just overview what we agreed to present. So I apologize for sending reminders too late. Maybe some of you were just waiting for reminders, and in this list not everything is shown. So I believe we are not doing
I have a one slide,
okay,
little brief intro to that.
Okay, then we do a little. Thank you. Then we do a little change on the go. Okay. So Hadassah, you will be speaking second. So just you have 5 minutes to prepare things. How are you? Very happy to see you. So we will start with Joseph Granlie. So he never ran electronic structure calculation in VASP until last week. So it will be his debut, and he will immediately teach us how to plot orbitals. Okay, then Hadassah will tell us how to integrate the orbitals, because they are later on, some of us are going to pursue electron transfer when charge is being transferred from one spatial area of a model to another one. And typically there is an axis along which charge is getting transferred. Therefore, motion along, let's say, Z, direction of charge transfer is important, and along X and Y is irrelevant. and Hadassah will just will provide us overview. Spectra without spin, I believe the presenter is not here today. Let's put it at the
bottom and mark it as postponed.
So if some subjects are not presented, just look through the manuals that were distributed a week ago, or request. We can cover them one-to-one, or one of the senior group members can share skills in one-to-one meeting, but we need to rush forward with other skills. I'm just surprised to see David on the left side, both in person.
I've been playing with trying to figure out how to get the mic working. I think I might have figured it out.
Oh, okay. Thank you. Thank you. It's really,
But
really
I
great.
wasn't going to try testing it until we were done talking.
Okay. So then David will teach all of us several skills at once. So those of us who were taking computational chemistry class, or those who just started, noticed that there is no spin. There are just electrons per orbitals. And in fact, one can monitor and specifically lay spin up or spin down, spin alpha, spin beta per orbital, or hello, August, nice seeing you connected. Or one has an advanced tool of allowing a mixture between up and down spins, which is takes place for heavy elements where electron angular momentum is high. And there are ways to account for it in the software that we are practicing, and David will basically teach us how to run the calculations that take into account this aspect. Okay, then William, who has also started running VASP very recently, maybe even less than a week, maybe 2 days ago, but he will teach us what is momentum of electron and how to control it in VASP calculations. For majority of us, it is of secondary importance, but for in solid state projects where there are nanostructures or solids which are periodic, infinite periodic models, it is a critical skill that it is unavoidable. So it's and then the presentation by Sarah will be most important, of the highest value presentation for today. So she will teach us about how to run jobs for heating and molecular dynamics, which she refers to as NVT and NVE ensemble. And after listening to her talk, after we finish our meeting, everyone is encouraged to follow her instructions and run similar jobs in your directories. The outcome of these runs will be needed by the next week. Everything we will do from now on will be based on molecular dynamics trajectories. So many things are optional, but this is mandatory. So if something doesn't work, if you try to run, it doesn't work, send email to me or like to the whole group. We will try to help as much as possible, because the plan is that everyone will have molecular dynamics trajectory in a week from now. Sarah, you have a big responsibility of helping everyone. Thank you for doing it. Then August, I admit I didn't open your slides, but I saw you send it. So I hope very much that he will teach us how to plot spaghetti plot, which help to analyze molecular dynamics and reflection of molecular dynamics on orbitals energy. Then Peyman will, so it's like cooking plots, spaghetti plots and broccoli plots. So Peyman will teach us how to visualize molecular dynamics in one image. And at the last but very not least, Meade will teach us an advanced skill that originally was developed by Dr. Han Yilun here, and Meade was just learn from him and practice and continue development. So this is important and interesting skill that stays a little bit away from the mainstream. We all will be focusing how the nuclear motion affects electronic motion, right? And this sub-chapter focuses on how the change of electronic state affects nuclear motion. So by exciting system, it starts moving on its own. So in some projects, it can be useful, maybe in Adam's project, maybe in some others. So please correct me if I miss someone or if I included someone who doesn't feel ready today. Okay, so no one corrects me. What I'm going to do, originally I was planning to share all slides with everyone. Probably I will do it retroactively. Now we need to just stay in time. So the little plan is as follows. I will stop sharing. I will enable all speakers to be co-hosts, and then we'll go along the schedule with the first presenter, Joseph Granlie. So just give me a couple of seconds to make you a co-host.
Can you hear me? Anyone online?
I've got to join into the Zoom link, so.
You can hear me, August?
Yep, I can hear you just fine.
Can you still hear me?
Yep, I can still hear you. You're all good to go.
Oh, Adam, thank you for joining us. Okay, let's make sure that we are on the record. Yes. If anyone noted the recording has stopped, please give a signal, because on the previous meeting suddenly it's, the recording stopped in the middle and we didn't have the whole story.
Okay. I've got the mic working for
Oh, okay, yeah, thank you so much.
Should I keep my computer then?
Huh?
Should I keep the microphone on my computer off then probably and just kind of go through the room?
Okay,
Or
you can, any speaker may try, it doesn't allow me to assign co-hosts. Oh, I know what is going on. I'm connected from laptop as a co-host. I need to go from here. First one.
is that supposed to be?
Being this co-host now. Silent is co-host now. Is co-host now. Co-host now. everyone is focused, right? Okay. Okay. Now, could you please try to share screen? Oh. Okay, just tell me whatever you like, with an idea that you are teaching all of us what are the orbitals, why do they need to be included, and how do we start it.
Yeah, can everybody hear me? Yes.
It's a little bit quiet, but yeah.
I'll try to speak up then. Okay. I'm visualizing orbitals using VASP MD or VMD. That's what we're doing. So the first trick is to use VASP to actually calculate the par charge file, which will contain the information about the orbitals. So basically what you have to do is you have to optimize the position of the atoms using VASP first. But I'm going to assume that we have a postcard file that's already optimized. Then what you'll do is you'll use an in-car file, which will tell VASP what to do and what methods to use to do the calculations, which you can see in this picture. The important tags or values to pay attention to are listed here. The L part is indicating that we want the data to be written to a par charge file, so we can actually use that. The LSEP is so that the charge density for every band or orbital is calculated separately instead of together. And then the N bands is just telling the program what number of orbitals or bands to do the calculation for. And EINT is specifying the min and max energies in EVs of the specified bands. So then we can run VASP using a command, I guess, close to this bottom right corner of sbatch query regular.sh. When you run that, the output will be a par charge with band number and then an all K file. When I first did this, I thought that we had to convert this to a Gaussian cube file, which we don't actually have to do, but if you want to do it, here is how you do it. But we'll just kind of skip that. So then once we load into VMD, the first trick is to load in the two files, which is the two pictures over on the left. So you get a file and then new molecule, and it pulls up these two windows. You want to make sure that you have load files for set to new molecule instead of an already loaded molecule. And then you browse and select the file that you need it to be. This top one is showing the postcar file, which contains all the atom positions. And then for file type, you just select VASP postcar. And then it's a similar process for the par charge file. If you converted it to a cube file, then you want the file type to be a Gaussian cube. Otherwise, you want it to be a VASP par charge. And then over on the right, we go into the graphics and then representations. On the left-hand picture, we have the selected molecule of just being the positions of the atoms. So the important parts here are the drawing method. We want it to show bonds because that will show the bonds and show the actual structure of the molecule. And then the material, you can change what it looks like, I guess, but I just left it as opaque. And then the bond radius in the lower right, you just kind of want to shrink that down so it's not super cluttered and hard to see. And then we select the par charge file and we convert the coloring method to color ID. And then that number 0, you can change the actual color of the orbitals you want it to be. And then we want the drawing method to be isosurface, which to my understanding is related to the probability density of finding the electron inside that surface or volume. We can change the ISO value so that we can choose how probable we want the electron to be, I guess. And then we changed the draw method to a solid surface because if you leave it as dotted, it's really hard to see. And then you can change the material again, opaque or transparent are usually the two that are used. And then here's just a couple screenshots from VMD that show what these orbitals might look like in an example. And I guess that's how you visualize orbitals.
Okay, please join me in thanking the speaker. So any questions, criticisms, suggestions to improve?
You want to go back to the previous slide?
This one.
Yes.
Yeah.
So in your graphical representation for the postcard middle
Yep.
picture, you ignored coloring method.
Yeah.
Should we worry about coloring method at all?
Depending on what you want to do, you might want to change coloring method. I'd have to load it up to see what other options there were. I left it as just coloring method name.
The most useful one is element.
Element. Okay, all right. I'll take that into consideration.
So we use, if you go to the next slide, would be.
Yep.
So are you just showing like your negative orbital here, or these negative and positive, just the same color?
So these are the same orbitals, just different orientations of the molecule. I'm not sure what you mean by positive or negative orbitals though.
Like are they both low?
So it's charge density, it's not wave function. So it will be not vertical. Okay. It looks like Haley wants to ask, but not sure. No? Okay, one slide back. And maybe one. So most of us were doing partial charge densities, but question to William. Did you do the step of charge to Q when you were processing your orbitals, or you skipped it?
Can you repeat that one more time?
So right now on the first line in the black cube, there is a charge to cube.pl. Did you ever do it for your orbitals, or you skipped it?
I just kept it.
Okay, anyone else who was skipping it, or who was doing it? Like, who was doing it charge to cube to both orbitals? At least once. Who was doing orbitals always without this step? Okay. So yeah, thank you. So now let's go to the next one. Yeah. So the charge to cube establishes equivalence between output of VASP and output of another popular computational code Gaussian, brings them to the same form. But this conversion is needed if you do not have DMD and if you want to use Gaussian. The beauty of DMD that it, well, it's maybe doubtful beauty, but it allows to skip this line of conversion. So the VMD allows to directly read or charge OK without the view. So it recognizes the internal format of VASP. And if you need to vote like 100 orbitals per day, maybe you want to make it one short, one skip. Yep. Okay. Any other comments, suggestions? Everyone can follow the teaching of Joseph.
Yeah, I guess I just wanted Joseph to comment on projections as well. So like orthographic and yeah, perspective.
Yeah, so I guess I don't know like the actual like definition between the orthographic and stereographic projections. Or perspectives, sorry. But in here, I believe I was using the orthographic, which just kind of makes it a little bit easier to line up like crystal lattices, I guess, because you don't get like the weird going to a point sort of like perspective lines. So it just makes it a little easier to view. Yeah, that's the one I used.
Yeah, just for brevity's sake, the way you can think about it is like orthographic doesn't have any parallax, whereas projective or perspective has parallax when you're actually like looking at the figure. So it can be a little bit more helpful if you do one or the other, depending. And then also one last thing, what about coloring conventions on orbitals? Like when you're doing figures?
Yes, so the coloring conventions are, you want to use blue for HOMO states, and you would want to use red for LUMO states. And if you have the SOMO states, or the singly occupied, typically green is used. So that's kind of the convention here. And here we're visualizing one of the HOMO states, which is why I was using blue.
August, are you satisfied with the answer?
I'm satisfied, yeah. Is everybody else satisfied with that?
I think everyone is satisfied.
Okay, good.
More comments and questions?
I'm just curious, so what is our system? Is this silicon carbide?
Yes, yeah.
Oh, okay. Everything is clear, so let's thank Joseph once again. So you probably stop sharing. Hadassah, you're ready to start sharing? Okay, so if we ever need to analyze charge transfer, we may want to integrate, and Hadassah will teach us how to do it.
All right, so can everyone online hear me?
Here in the room, we definitely can.
Okay.
I have turned up the volume on the mic to max, so hopefully.
Okay. So I'm presenting on the integration of electron orbitals, three-dimensional to one-dimensional. Joseph presented how we can make part charge files and visualize them. So this is the next step that works into charge transfer. So this is just like an overview of what the end product is. This is just pulling some slides from a project I did in the computational chemistry class last semester. With the left, you can have like what a 3D orbital visualization is for different HOMO lumos. Then on the right side, it's compared with 1D orbitals. We'll get back into what that is later. So a little more background. We're doing these electron orbital visualizations with density functional theory. Looks like the electron density. When we're talking about the cone-shell orbitals here, it's kind of like band structure for physics terminology, if anyone has some familiarity with that. These visualizations can help us see if charge transfers occurring between a HOMO and LUMO gap on different materials. And all these calculations that I'm walking through have been calculated in VASP. This is just looking at a directory that's on the NERSC. It's a super computer. At this point, assume you've already computed all your part charge files. There's a couple different scripts you can use to do this 3D to 1D integration. One that I used for my project was this one called band integrates VASP. It's pointing to with this orange arrow. The outputs you get once you run the script are these .c files. See a little more of those in a minute. So with this band integrate V, once you have your part charge files, you enter the orbital number from your part charge file that you want to start, part charge to finish, and then it'll, in a few minutes, you'll have an output of your .c files. There's another option, NERSC band integrate VASP5.pl. I did use that one when I was writing these calculations. I'm not familiar with the inputs and outputs of that, but that is another option. So in these .c files, we have these different bits of data. In order to visualize them, you can plot them in a GMU plot terminal on either on Photon, which is the industry chemistry server, or some other supercomputer. When I did that for mine, this is just a zoomed up view. So this is looking at the HOMO LUMO for something in my project. We have the position, seed angstroms represented on the y-axis. So this is just representing if I integrate across the y and the x dimension, like what the density is with respect to the z dimension. X-axis, we can see the z dimension. We come back to what I did for my project. We have these 3D orbital representations on the left, 1D on the right. We can compare and contrast like two different scenarios where there's two nanocrystal materials that are are further apart versus closer together. So this is when they're further apart. That's when they're closer together. But look at this further apart one. So in this, this is comparing the A and B are representing the HOMO. So you can see like in the 3D version, the charges were localized on the HOMO side, and then the LUMOs were localized on the southern nanocrystal. And then you can see that in the 1D representation as well. So what we want to look for when there's charge transfer is that between these HOMO-LUMO gaps, there's more shifting between the 1D representations, which we can see a little more on this graph. In 3D orbital representation, you can see that the electron density balloons are moving around more, whether it's on the HOMO or the LUMO. And then on the 1D graph, you can see that there's a shifting around of what the electron orbital density is. So that's a really quick crash course on 3D to 1D orbital integrations. I'll open it up to questions.
Okay, please, gentlemen, so would it be sufficient to reproduce the skill, or there are some questions? Yep. What question? Anyone? It looks like it's crystal clear.
Oh, I do have a couple questions. Yeah. So, firstly, can you change the axis that you choose with respect to this graph? So, like instead of using a z-axis, would there be like a way to change the axis for your graphs?
It's a good question. My guess would be that you'd have to work in the, modify what's set up in the integration scripts or dot field that's been created. The ones I have were default set to integrate across the z-axis. I guess, Dimitri, I think you wrote these .pl scripts. Is there a way to switch to the z or the y or x-axis?
Thank you for the question. Thank you, Hadassah, for like sending the ball to myself. Yes and no. Practical problems sometimes need to look for charge transfer along different axes. But it's so boring to write. It's much easier to just rotate the model by 90 degrees, and then identity of axis is changed, and you run the same.
Okay.
So when you convert XYZ into postcard, there is a step based rotate XYZ, and then you do 0, 0, 0 for rotation along X, Y, and Z axis. If you would put like 19, 0, 0, if you rotate 90 degrees along X, if you swap Z and Y. Right? If you do 0, 90, 0, if you rotate along Y, and if you swap X and Z. And by swapping X's and then redoing altering structure and redoing orbitals, and then practically in the script, it will be what you are asking me and what August is asking you.
All right. Thanks.
And then just as a side comment, be sure that you change your axes labels, like your axis labels, when you do that, and make sure that like it's crystal clear, sort of what axis you're looking at. You can do that by, I believe, vimming into the Perl file that you have here, and then you should just be able to change one letter, and then you should be able to get it. Because I'm pretty sure this uses GNU plot, right, Dimitri? Okay, yeah, then you should be able to just vim into the Perl script, and then you can just change the axes titles. So, and then sorry for one last question. How do you determine charge transfer character using these graphs? Just quickly.
I guess the main thing you're looking for is that if you're, for example, just looking at the HOMO itself or the HOMO -1, like is the density moving around? So this is an example, like in 3D orbitals, you can see there's a shifting, but you can see a little more quantitative example that's shifting by seeing how it's moved around on LUMO versus LUMO +1, HOMO versus 1. I also have some graphs when you just have HOMO LUMO themselves intersecting. Let's just see, I can pull up another thing from one of my projects. So like this is another visualization where I have the HOMO LUMO themselves. And you can see like in the case, this is right, is the case of two where they're closer together. There's a little more intersect here versus on the left where we have when they're further apart and the HOMO LUMO aren't as, there's not as much density. So I guess this is another way you can visualize the charge transfers happening, just looking at how the HOMO LUMO gets shifted around on the 1D charge transfer. Does that answer your question?
Yeah, that's fine by me. That sounds great. So thank you. I appreciate it.
Meade, would you like to add to this answer by telling how you, just by words, how you computed the distance between centers of orbitals, either by speaking or typing, if you feel comfortable? Connection. So at the end of last meeting, Meade was presenting how he adds a descriptor into analysis of orbitals by finding the XYZ center of mass or center of charge for an orbital, right? If you remember. So at least one person remembers. And then if you have two orbitals and you have coordinates XYZ, its center of charge, and you subtract them, it will give the value of dipole. So if these centers coincide, there is no charge transfer. If there is a larger distance, if the value of dipole is bigger, it means it is a larger extent of charge transfer. So it can be achieved either by localized orbitals being far from each other or delocalized orbitals with just imbalance to the left and right side. Okay, and one more question that I asked and David answered. The version of the script that Hadassah did present provides an output in form of little individual files for each orbital. Is there a way to combine them in one big file that will include all orbitals?
I looked at the group chat and I saw David's answer.
Right. So it's basically the same script, but it writes this information about integrated orbitals in one big file. And later on, in 2-3 weeks from now, we will use it. So in addition to what Hadassah taught us, please look at the name of the script that David added in the chat line. And the output file that contains everything is bent out without extension.
Put the name up
Hmm?
so we can see the name of the script.
Right there,
Oh, wait, where? That one?
right where the mouse is.
Okay, yeah, thank you, Hadassah, for highlighting. Joseph,
Could you just talk about like what the output of the .z file is, or like what it contains, I guess, in its structure?
I quite frankly, I just opened the C file up because I plotted it, but I haven't looked into it myself. But what I think is that it gives information about the density and the positions in angstroms. So let's see.
first of all, this position coordinate along Z. Second is the value of Cherokee. And the third is normalized Cherokee. Yeah. Okay. So if you hate Plot and want to download it into your like Microsoft Excel, you can just put versus. So,
Is there anything special about the extension, file extension .z?
no. It may overlap with one of the system times, but just Z instead of X or Y.
So if I like revote it, plot along X, I can change it to .x.
So any questions, more questions for Hadassah? Questions one, questions two? I forgot how to count. Let's thank her anyway. So Hadassah, you may stop sharing. And I believe the next glorious presenter is David.
So my first slide here is looking at hybrid functionals. And I didn't put a lot of effort into it because I've only done it a couple times. But you can just add tags to the in-car to specify other orbitals. So this is just a screenshot of the wiki giving some tags that you would need if you wanted to use HSEL6 or O3 or others. And there are more than just these ones as well. This is what I took a picture of. So you would need them. If you wanted to do HSE06, you would need to add these tags.
Do you allow to interrupt in the video?
Yes, that one.
Oh, okay. So LHF calc. So in this long and crazy abbreviation, what HF stands for?
Hartree-Fock.
Why we need Hartree-Fock if you're doing density functional?
We're adding a portion of the Hartree-Fock calculation back in. That's where the hybrid
Okay, yeah,
comes from.
I totally agree.
So that this HF screen is discussing how much you add back in. If I remember what that table does.
Okay, I think it is perfect. Do Stephen or Haley want to add anything, any spice to this answer? Or you totally agree? Okay, so there is the DFT method, there is a Hartree-Fock method, and one can do a little cheating and blend them together at certain proportions and get better agreement with experiment. Okay, and so it is what is going on. Okay, so continue.
So now we're moving into the ground state spin orbit coupling calculations. So you need your standard in-car input files, postcar, in-car, K-points, POC-car. In addition to those, we recommend, and we being me and Aaron, that you use the charge car from your spin polarized or spin restricted run. And you can also use the wave car from that, but it has to be generated using the VASP _std executable if you want to use it. If you generated it using the VASP _GAM or the gamma calculation, it won't work. It will generate an error. Otherwise, it's the post car is the conc car from your spin restricted, spin polarized run. K-point and POC car are the same. In car is a modified version of the one you used. So you use the in car from the spin restricted and spin polarized run, and then you add these 4 tags, or in the case of the last tag, you modify it.
Okay.
So. Yeah.
Oh, okay, thank you. Thank you for being generous and allowing to interrupt in the middle. So, as I suddenly noticed, we already walked from HSC to non-collinear, right?
Yes.
And what is non-collinear? What or when do we need it? What it is? I know it was not our goal for the day, but getting way words without equations and figures.
So non-collinear is allowing the spin to act in whatever direction it feels like. And it's a superposition of the alpha and beta orbitals.
Okay, so,
In a more mathematical terminology or physical terminology.
so spin is not,
Spin is not restrained to up and down.
it's not a good quantum number anymore.
No.
Okay,
So it's necessary primarily for large atoms, if you're using large atoms. So anything in the like sixth period or lower, and maybe even some of the fifth period. Yeah.
okay, sort of interrupting.
Yep. So the tags, the first tag, the LS orbit, that's what includes the spin orbit coupling calculations. The L non-collinear is non-collinear, includes those. I charge equals 11 is the tag that indicates that it should read in the supply charge card. The way we do it theoretically, I charge equals 1 should give the exact same result, but and NSW equals 0 indicates a single point calculation. So the other major thing that you need to make sure is you need to change to use the VASP underscore NCL executable, which is in your submission script right here. You are probably, if you're doing spin polarized or spin restricted, you're probably using, well, you're definitely using either the gamma or the standard executable instead.
Yep. I'll say briefly that you expanded needed. So some of us are just starting and maybe have only performed test runs on a photon server. And for hyperactivity, we are going to run on big jobs on the NERSC server. So there, instead of running the electronic structure code in a command line, it's not encouraged, but there are like 10,000 tutors, and it will just kill the company. So one submits requests for jobs into like cloud, and then it runs on other nodes. And this request is formulated in the form of this black box in the lower right. And what, oh yeah, thank you, David. And what David is focusing attention for, basically we can copy paste everything except last line. But the last line will have changes. So if the person who is running VASP is William, he needs to use VASP underscore STD standard. If it is like most of us who just do not care about points, who are thinking in a chemical way where electronic clouds do not move with constant velocity, we can use so-called gamma point, and then one can use VASP underscore gamma or gamma point for zero momentum. So it is just runs a little quicker. And if we all are good pupils of David, if we want to run this non-collinear spin, then it should be this VASP NCL. So although it is generated by the same company, those are 3 different executables. So changing a lot of group members in the past were trying to just change in-car file, run standard VASP, and complain about errors, which was natural. To run this non-collinear spin, it's programmed differently. Okay, sorry for interrupting. Add anything and just continue.
So this is the script that we use for job submission in VASP or in NERSC. The first line here would be the queue, nodes, time, name. This one is specifying K and L, which is a portion of Corey, cores, and then the executable. I think I covered everything. So if you are trying to, you need to use multiplicity in your model for this, you would need to run your initial job to calculate the charge car. You would need to use the spin polarized with the N up down tag, and the N up down tag sets multiplicity. So it does it work where 1 is singlet and 2 is doublet and 3 is triplet, if I remember. If I remember, that's the way the N up down tag, I would have to check to be positive.
Zero.
Is 0 singlet?
Zero singlet, 1 is doublet, 2 is triplet.
Okay.
The number of unpaired speeds.
So then you would just, once you get the result of the spin polarized run with the N up down tag, you would just use the charge card from that as I described in a few slides ago.
Question. I guess previously you said spin is not a good quantum number. So
Nope.
how did you specify spin multiplicity? Yes, can you answer?
Yes.
So, everything is, to my eye, is absolutely correct in what David is telling, but it is, it can be organized a little better. So right now, he performs a jump forward and backward. So he presented advanced method, non-collinear spin, and then he decided, oh, sorry, for a second, I need to return back to collinear spin, define what is N up down, and then return back to non-collinear. So it is, what he's telling right now is, to my understanding, it would work only for collinear spin with VASP STD or VASP down.
Yeah, so this would be the previous, this would be generating this file, the charge card that you would use. So it's not a terribly good transfer if you really think about it. But that's the way we've been working with it, is if it's got a multiplicity in our spin polarized run, we consider it to have carried through to the spin orbit run. But spin isn't a terribly good quantum number in our non-collinear calculations. But the thought is, because this is a single point, any ionic reorganization due to multiplicity in the spin polarized run won't change in the spin orbit run.
Does that make sense, or you still?
I also get really confused why we need charge call.
You do not technically need the charge car, but it makes it run much smoother.
There is a way to live the whole life with only non-collinear spin. And there are specific tags in the in-car which allow to manipulate with projections of magnetic moments, which sounds like L mod mom equals, and then you give the projections on mom, not mom, but projections on X, Y, and Z. It is written in the manual. It is expected to work, but it is very it gives errors and works very slow. And just empirically, we found a trick that David presents as the mainstream of activity. So different versions of that are different executables are able to inherit the wave function and charge density and use it as an educated guess to start self-consistent procedure. And at the beginning of each VASP line, the code is trying to navigate for the file charge car and wave car and read it from them and use it as initial guess. So if before running high level complicated calculation, we did something lower rank, before non-collinear, we do collinear calculation, then next step will work much quicker. In addition, there is a discovery by Aaron Ford that is included in his like a practical trick in his thesis, that one can indirectly define the multiplicity or approximate multiplicity of the calculation in the non-collinear spin by first doing what David is telling. Collinear spin with certain projection of spin on z-axis, and then just read wave curve and charge curve in the non-collinear, and then the projection is inherent. The magnetic moment is computed according to this value. So if any of us will try to go to a VASP Wikipedia and manual and try to find answers in these questions, it will be very blurry and not clear. David is showing a shortcut that practically works.
No, Megmon is a tag that you would use in the end car. I just typed it in so you could see what it was. So I was not expecting to be the first person to talk about DOS, so I went over it very quickly. So you need a healthy states file, which is the energy hop file from your run. And then you need to run the script address DOS, norm, and NCL from the bin. And it requires to know the number of states, the HOMO, LUMO, the number of electrons, what the Fermi energy is. There's a few things that I skipped over because I wasn't expecting to be the first one to talk about it. Which this code outputs the DOS.fermi Fermi file, which you then can plot using your preferred new probe script. So here I show a DOS that was generated for some model several years ago that I don't remember what the model is anymore. Any questions on it?
Yes. A comment. So those who just start, we are not focusing on this little purple thing right now, because we are going immediately to advanced. But anyone who does computational material calculation is expected to check, try each model by this little image, or which is needed to describe models with a lot of orbitals. So if they are
So I suppose I didn't mention that DOS is density of states.
so if they generate have almost the same energy, instead of drawing individual lines, one just combine them into a balance band, which is field, and conduction band is
So you check it using a picture, but how do you know if that picture is what we're looking for is correct? Like what should we be looking for?
You are thinking too deep. From common sense, from comparison to experiment and other calculations, if your material is insulator or semiconductor, there is a gap between occupied and unoccupied.
Oh,
If your material is metal, there is no gap.
okay.
And typically, when you start to exploring some model, you have literature, you have common sense, and if something goes wrong, you immediately see it.
Okay.
So to generate orbitals, it's basically the same process as Joe described. I think it was Joe that was doing that one. Joe described earlier. You just take your in-car and add the L-PARD, L-SEB, and EI and T tags, or if you want, you could also use the I-band tag, depending on what you're exactly trying to do. And it generates a nice orbital, which he described how to visualize. So this generates a par charge file that you then visualize. I used VMD. To do absorption spectra for spin orbit coupling, you need your input overlap file, which is going to be specific to your system. So it's this file right here. So it's 3 numbers. First number is the lowest orbital that you're interested in. Second one is the highest that you're interested in, and the last one is placeholder. You need the wave car, which is the output, one of the output files from the spin orbit calculation. And then we use the script here, read waveguard spinner healthy to generate the oscillator strength files. And here we have the oscillator strength file. So for the spin orbit calculations, the oscillator strength files are a bit different than they are for the other ones. For one, you see that we have 3 different types of files. We have one for valence to valence band transitions, one for conduction to conduction band transitions, and one for valence to conduction band transitions. And in addition, if you look at the order of columns within the oscillator strength file, they're in a different order. So the 6th column, this one, would be your oscillator strength file, or the oscillator strength value, where I believe it's the 3rd column in the other, the spin polarized and spin restricted oscillator strengths. So to actually create the absorption spectra, we need to first copy the valence to conduction band oscillator strength to the standard oscillator strength file name. And when you do that, it's going to keep this header line, which we need to delete to actually run the scripts that we use to generate our spectrum file, which is this script right here, the spectrum _imp SOC3. And it's going to ask you a number of questions, again, just like the density of state 1, how many transitions there are, energy range you're interested in, a broadening parameter, and what the HOMO is. And this will output the spectrum file. So then you're going to use your preferred new probe to generate the absorption spectra from the spectrum file. So if you look here, you see spectrum is the name of the file. And then this 2-3 indicates that it'll be an EV. If you open up the spectrum, which I did not add onto the slides, you'll see that there's several different columns. If you were to use 1-3 here instead of 2-3, you would get your resulting figure in nanometers instead of EV. So if we look here at my figures I have shown, these are the same. This can show you the effect of changing the broadening parameter. So these are all the same absorption spectra. I just adjusted the broadening parameter from 0.1 to 0.01 and 0.001. So you can see that as you decrease the broadening parameter, you get a more defined spectra. Any questions?
Is joining in sync and David? Okay, so does everyone feels happy and ready to do the same calculations from now on? If no, let's better ask David now, because we will be busy with other things very soon.
Is there a reasoning we wouldn't want to just always lower the broadening parameter to be like insanely low to get more accurate?
What is lower than broadening?
Well, maybe I misunderstood what you meant, but when you lower the broadening parameter, it gets more defined, which I just figured means it's kind of like more accurate or like true.
Okay, I'm curious to hear what David answers.
And that's not the case. I don't know.
Your observation is completely correct.
So you could keep lowering it, but eventually you'll just get sticks. Because we're giving a broadening to actually make like what experimentalists see as spectra.
Yeah.
Because if you, I don't think do it, but all these points are just generating a stick, and then the broadening factor is what is actually creating a curve around that.
Okay.
Perfect. So the idea is that we're trying to mimic experimental results.
Okay.
Lower it too much, it just looks like. try to describe it like a set model. It's just like a solid line of scribbles. It's like.
Okay. I was preparing my own answer, but you guys answered better. So the ultimate criterion of correctness of theoretical correlation is agreement with experiment. In experiment, most experiments are done not at 0 Kelvin, but at elevated liquid nitrogen. And then there are mechanisms due to temperature, energies of all orbitals are fluctuating, but we are not following this useful quick motion. And instead, we see just for experiment that all lines of board spectrum have these shapes. So we need to do any cheating work, any adjustments to our too precise experiment, maybe a little blurry and reproduce experiment. And there is a background of this. The higher the temperature, the more uncertainty of energy of each electronic orbital. So what David is offering is just the way, again, he's very brief, but he's providing us several shortcuts. In addition to main tasks, he shows how to mimic experiment in most optimal way. Yeah. Do you think it's clear enough? Will you be able to rerun?
Dr. Keller, I have a basic question.
Please.
Yeah, because this question kind of seems simple because the concept is not clear for me. So when we solve the Schrödinger equation, the energy eigenvalues that we obtain are quantized. So my question is that why we have such continuous figures, both for absorption and US?
Yeah, thank you, Peyman. I think the discussion went to our last thing rather than practical aspects. So, Peyman, the energy of electronic orbital is well defined when your ions are frozen, not yours, but your ions of your model. If you cool down the system to like liquid helium or absolute 0 Kelvin, as soon as we heat up the system, ions start to move. And as soon as any little ion is moved, the energies of all set of orbitals are changed. And if you want to represent the spectrum in average over a certain interval of time, we need to account that all ions were moving and all energies were a little bit bigger or a little bit less. And there are precise ways to do it, and there are approximate quick ways to do it. So David was offering a quick way to take into account of this thermal broadening. So just artificially add a width to each optical transition. Does it make sense to you?
Yes, perfect. Thank you.
So Hadassah, do you feel comfortable reproducing non-collinear calculations for all your models based on this instruction?
I'll need to go through the instruction again, but yes.
Okay, so nothing suspicious.
Not damage.
Okay. Will you be able to? We hope that David is in the same room and you can just ask him.
That's the question.
Will you be able to compute density of states and spectra for your porphyry models with spin orbit coupling? So instructions were clear and you don't have detailed questions like what would you?
Nothing that comes to mind.
Oh, okay. Yes. Okay.
I would want to make sure he was in the room.
Okay. Once I was passing an oral exam, examinator was asking us like, can you repeat the specific calculation, which was very advanced quantum thermodynamics? And one of the classmates told, yes, in presence of a specialized literature. Okay. Anyone else wants to ask questions to David? As I understand, primarily based on his talk. This one. You can type in the chat line if needed. Questions two. So before I say question three, this spin orbit coupling and hybrid functionals do not typically change dramatically results that we generate, but they make result that we compute a little bit more better comparing to experiment, better agreement with transition energies, and you may want to add them to your arsenal if you want to increase chances of your future paper to get accepted quickly. Okay, question three. None. Thank David once again. Okay, so yeah, very happy to see London. I didn't access the chat line. How was the trip?
It was pretty good. Everything went pretty smoothly. Didn't have any issues on the way or anything. Now that I'm here, I already have a mountain bike and some hiking shoes and stuff. So I'm pretty well set to live in the mountains for the next 3 months.
Okay. Did you already get the badge to enter the facility?
Yes, I got that today. It only took like 2.5 hours.
Congratulations.
Yeah.
Okay, would you be interested to, will you be available to give presentations on these meetings, or you expect to be overloaded?
I think I probably could.
Okay, I'll keep it in mind.
I mean, I don't really have like a good feel for, exactly how busy I'm going to be quite yet. Because I've mostly been doing like orientation stuff so far, so.
Okay, yeah, thank you. So let's see who is the next presenter. So I believe it is William, right?
I thought I was ready, but after seeing others,
Do not worry, just show what you have and allow others to guide you.
So Landon, while you're here, I took a look at your computer again today, along with some of the students here for the summer. And I believe I have reached the same conclusion that you did, that there's an issue with the motherboard.
It seems either the motherboard or the processor, because if it's not even getting to the BIOS screen, like those are the only things that have done anything at that point.
I believe it's the motherboard, and I think it might be that when we plugged in all of the extra stuff, the new fans and a new hard drive, we might have overloaded the really tiny power unit.
Could be. Did you try to like unplug everything? Like, does it work after doing that?
Well, we tried that, but from what I have read, once you like fry the motherboard by overloading it like that, it's done.
No.
Oh, it's $200 for a new motherboard. Basically, any new motherboard is $200.
Yeah, sounds about right.
So I'm going to be doing my presentation on momentum dispersion, and graphing our band gaps as a function of momentum. There we go. So we're using the VASP software, and for these ones, we care about our K points, and to generate them, you first give it however many K points we want. We want them to be on a line, and then we set what interval we want to look at them on. And then we use our POSCAR, PODCAR, INCAR, K point test, and then test. And then we end up doing more position. And then it'll give you a bunch of lines. You end up just pretty much scrolling to the very end. Because it isn't until the very end where it gives you the K points. Where it'll give you your K points. And then you can then look at more of like each individual one, where it gives band number, the band energies, and the occupation of each one. And then we're able to then graph that. And then our band gaps is a function of momentum. And we can see that it's like a wave-like. Some stuff I noticed is that I put these bars where at a lot of points where it wasn't differentiable, besides where the green and the yellow, which I thought was interesting that it wasn't differentiable anywhere else at these points. And then we also have these points of orthogonality at these turns, which I also highlighted. And then I ended up creating models for it for K1 and K2. And then we can see that they end up being the same. And that's because we're only looking at the magnitude of our K instead of the vectors. That's what I have.
Okay, Ms. Jenny, thank you. Keep your slides online. So, any questions to me? Probably question.
Yeah, I have one.
Yeah, please, Meade.
Yeah, can you explain what you mean by K point?
I can do my best. A K point, from what I remember, is part of a reciprocal lattice in the real, so the non-complex space. It has to do with momentum. Is my best understanding of it.
Okay.
Okay, yeah, let's try this little game. So, Jennifer, what is a K point? Just based on listening to
Well, I'm kind of in the same boat as Will. From what I remember, it is a reciprocal space, like of your lattice. And I believe that the K point was related to like the position or the momentum of like an atom at a certain point, but you transferred over to reciprocal space. I don't remember exactly. We didn't do a whole lot with it.
Okay. Let's refine Hadassah. I know it was not part, at least in the class that we attended, but maybe from general background.
I am trying. I guess for me, I'm thinking about like you have a lattice structure, the K points relate to that, like there are points in momentum space where I guess where the X and Y and Z coordinates all match. I don't know. It's like it's some periodic structure.
Okay.
Space.
Yep. We are moving in the right direction. There were no wrong things. London, would you like to add to the to this party or to this party of riddles?
I would like to, but I don't know if I have anything really useful to add. It's been a long time since I've actually like worked with them, so they're kind of fuzzy in my memory right now. But yeah, it's definitely, there are points in reciprocal space. It's sort of like different values of momentum. So it's, yeah, it's something to do with periodicity. And like, if you have like a smaller system, you need more K points, but if you're modeling a bigger system, you need less K points, I think.
Okay. And anything, you do not need to rely on any your calculations without train structure. You can just bring something from the course you recently taken about solid. I think it was band structure, dependence on momentum. I remember you were doing homework about Miller indices.
Well, we never really, we basically went over, you know, like here's what a lattice plane is and blah, 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 but we didn't really talk about K points in that class. Because it doesn't, I don't know, I guess as far as I'm aware, it doesn't really come up with like X-ray diffraction and whatnot. Because that was, I guess the focus was, you know, like materials characterization.
Okay, that's fine. Anyone else?
Dr. Kirin, is it as same as the, for example, K points can describe the surface, the plane of the crystal using specific coefficients?
Well, it deals with momentum. So it can, if you are speaking about specific plane of a crystal, K point may relate to orientation until it is motion of electrons perpendicular to specific plane. So it's orientation in the space of vectors. Steven, you want to add?
So I'll take a stab at it. Someone please stop and correct me, since it has also been many years since I've actually read real literature on this. But my understanding of the simplest way to conceptualize a K point is that if you are working with a periodic system, such as a crystal lattice, and you calculate a wave function for that system, it will be the points that, if you visualize it as a particle that wave function as a particle in a box, it will be where your wave function is 0. It'll be the boundaries of your box. And so if you map that into reciprocal space around your function, you will get a series of points through the system, which are all equidistant from, I want to say the center of that sense, from like your starting point, and those lines that you could draw through those would be like your Miller indices, correct?
Okay, so one can scan over K points and make the directions of your scan associated with your indices. Can we go forward? Yeah, this one. Yeah. So if we would think as chemists, we would stay only on the x-axis equals 0. And x-axis equals 0, these colorful lines would correspond to energies of different orbitals, right? But if the system is periodic, if it is not isolated by a vacuum, there is a chance that the wave function or the orbital, certain orbital, will not stay localized on certain atoms, but will continue to move, jump from one atom to another across the border and then repeat. Right? And the measure of this velocity, of this momentum of the orbital moving at the whole entity can be in 3-dimensional. Kx, ky, kz. Therefore, it is one point in k space. So it's where the orbital is moving. It can move along x, along y, along z, or simultaneously in several directions. And it can move quicker or slower. And depending on how quick or slower it moves in a certain direction, the orbitals not just slightly adjust, they can dramatically change the electronic structure. What viewing is showing. So the gap is dramatically changing from like 6 electron volts to 0 and backwards. And in periodic lattices, if you are not dealing with nanostructures, if you do not have vacuum, it is like true periodic structures. It is critically needed.
I did have a question about, so in physics, we treat momentum as a vector usually. Yeah, even though it's a pseudo vector technically, but do you do that in chemistry, treat it as a pseudo vector rather than just being a normal vector? Or
what's the difference between vector and pseudo?
For I remember it's a pseudo vector, it's not conserved under a transformation of like, so a normal vector, I'm pretty sure the magnitude will stay the same under a transformation, while a pseudo vector will not. I was wondering in chemistry, would you, but like usually in physics, we don't usually use the transformation. We just are always in the same space. So I was wondering in chemistry if you do that.
So I need to ask you more which transformation you keep in mind. Like if there is a translation, then yes, it will stay the same.
Yeah.
But if there is a rotation, it's very doubtful because the symmetry of crystal will change dramatically. So I do not have answer. Translation, yes, others I don't know.
It's actually a pseudo vector basically changes to the opposite orientation under a inversion.
Okay. So any more questions or comments on beautiful chapter of momentum of electrons? Okay, points? Yes.
I'm not exactly sure I understood how to generate this plot.
It was assumed to be shown, but it is skipped. So there is a set of scripts where you just process out car and extract this information. Can we go back? So right now we do not have time for this. No, forward. Yeah, this one. So do you see the black box on the right? So it is a list of orbitals for key point number 1, right? And the output generates as many such boxes as many key points are used in this calculation. So we would need to extract all energies of orbital number 10 from each box, and then plot their energy as a value of as a function of k point. And there are scripts that do it. Make sense? Okay. So yeah, thank you for asking. More questions to give them? Questions 1, questions 2, thank you once again. So you can stop sharing. Let's check who is next in the program. So next speaker is Sarah, who is presenting most important talk of today. Sarah, would you like to share a screen?
Yes, sure. Okay, hello everyone. So we're gonna go through how to heat up a system and start molecular dynamic simulations. So here's just the basics to equations. It's basically just to know the number of nucleus, the temperature, and then Newton equation. It's very simple basic set, basic background, and then as many other different type simulations, we first optimize the system, and we expect we have the postcard, which is the count car, and then copy it to a postcard, and then you'll keep the postcard the same and key points if it's not that big, and then copy your in-car for heating from your server to do the heating, and then after we do the heating, we will go and copy everything again and copy the MD in-car and then do the MD simulations. So let's start first with the main keywords. So there are different algorithms can be used to do MD simulations. There is Andrews and Noshover. These are the two famous methods, and ensembles that is NVE, which is just keep everything constant for the temperatures, maintain temperatures constant, and also NVT, and of course the MPT, which is keeping the pressure and change of volume. So these are the main general for the method keywords, and then there are a couple of more keywords. So the Iveron, which is the one we use generally, Here we're gonna set it for 0 for however method we're using. MD algo, can you see it here? So it can be 1, 2, 3, 4, depends on the theory you're using. But here in our system, in our default input cars, for MD simulations, either heating or MD, it's kept default, so it's not mentioned in the in-car. So that means we're using standard molecular dynamic simulation. The S mass, which is also very important, this one specifies how you're gonna control your temperature. This one will be different for heating and MD simulation. Votim and NSW specifies the total number of simulation time, where votim is just the side of the step, like how far you're gonna move every time, and how many times you will do that step. That's why the total simulation time is just the multiplication of both of them. And of course, temperature begin or temperature final, you should specify it as a desired temperature. So here you're gonna start with the heating. So to heat our system, again, if you're gonna look quickly here, the iron is 0, as we said. S mass is -1. That means let's try to control the temperature and keep it as constant to the desired temperature as possible. And here we specified very big bottom and very small SW because this is just a test. So we do not care about this too much here, but make sure to specify bottom as small as possible and SW as big as possible. And ISIF is 2. This is almost the default for all MD simulation we're gonna do, and MD alog is not mentioned again because this is standard MD simulation. To submit the job, use the bot car, of course, key points, and count car copy the bot car from the optimized simulation. Here's a tab. Make sure you delete the velocity from the end of the bot car. So when you copy the count car to bot car, open it, and you will find the coordinates of the atoms, and then 0, 0, 0, 0 columns. Just delete all of them. These are the velocities. It will help you get more saturated temperature. So here is the submission script. Basically, you can start with the debug just to make sure it will run instead of waiting for days, and then you figure out you miss a file, you miss something, and then you specify the number of nodes you're gonna use, which is you're gonna multiply by 46 the number of cores you have in every one node, of course the time and the name, and that's it. Once you submit the SPatch file, you will get your simulation running. Once it's done, the heating just grab the temperature from your car and then plot them. As you can see here, we heated our system to 2500 degrees Kelvin, and it looks like it's saturated, as you can see at the end, the last 15 steps. Next, you're gonna take the count car generated from heating, and then generate a new folder, add your count car, key points, bot car, and then copy the in-car for MD simulations. So here the the S mass is different. The other one was different value. Here is -3 because we're using microkinetic sampling. So this one is MVE, as we said. Again, the MD analog is not specified because it's standard MD, and the bottom here is very big. Just ignore these values here. You have to set it in a better values. So let's proceed with this. So here, once my simulation is done, I will need to look at the total energy, the temperature during simulation, and mean temperature. So here I'm grabbing just from the output files and set them in data files, and then I will plot them easily on the server. So here it looks nice. So everything is saturated, everything looks stable. So this one I didn't do manually, but so 1 second. So why I need to copy count current to score? going from heating step to MD step. So I need to copy the velocities. So once I have my my count car here at very end step, which is at the desired temperature here, for example, it's 2500. The velocities at the end of this count car will be the desired velocities at that temperature. So once I copy that and do my MD simulation next with the same, of course, temperature, not 300, with a 2500. So my system will be starting with expecting temperature equals to the respective velocity of the ions in the system. And then also one of the analysis I found when I was reading some previous tutorials or exchange experience, I found they can be used to check your HOMO-LUMO energy variation during time from your MD simulations. It looks interesting, but honestly, I didn't do it. So this is how it can be done. I guess this one is spaghetti plotting, I guess, I don't know. So, okay, so if I need to do videos for my simulations, so just copy your per file and then just run the per file, and then you will get a movie.xyz. You can plot it directly on the server, like I guess I did before. I don't remember it's Nurse or the other server with first login, but we can do it quickly on the service like that. However, you can still do it on VMD. Just download your file and then open VMD. Once you load your, once you go there, you go for extension. Once you load your file, and then go to extension to generate a good video for application, and then use Movie Maker, and then from there you can specify a format as specified here, and again you can set the title or other if needed. And yeah, that's all I have.
Okay, thank you, Sarah.
Yeah.
So any questions are very welcome and appreciated. Sarah, please do not remove your slides. Go back a couple of slides to remove the questions.
Okay, I'll keep it.
Since we all are expected to repeat these steps within next week, so just look through slides and ask any questions if something is not clear.
I have a question. So you mentioned there's different ensembles. Like, is the default ensemble and all the molecular dynamics files sufficient for what we're doing, or do we have to worry about manipulating that?
Okay, let Sarah answer it, and later I can add a comment.
I didn't hear the question clearly. The voice is a bit far. So you're asking about the default ensemble?
Yeah, like, do we need to, I think like the SMAS, your later molecular dynamic file was sent to a certain one, like, do we have to worry about modifying them for a project, or for what we're doing, is it okay to leave it, or it depends?
So personally, I prefer to use NotHover. So this one is being used in literature and generating good results in experimental results of desired targeted simulation. So this one here, NotHover, but as a standard, which is even on VASP website, I found they're saying that MD standard MD is kind of outdated, but however it's still working. I tried to test before for different thermostats here, and I didn't see a big difference between them. However, it was only the different I was checking is just the temperature fluctuation and saturation at the end. So, but again, from literature and from my project literature MD simulation, I found they're using NotHover, so that's why I will use NotHover in my simulation, and I will use NVT sampling, because MVE can be skipped. So by just copying the count car from the optimized simulation, remove the velocities, the zeros velocities, and then run NVT simulation using no solver, and then just skip the first 100 step or 200 steps using any simulation code or any analysis code can ask you to just ignore the first 200, 300. So just consider the saturated temperatures, and then you will skipping the heating, and you will skipping using standard and using two different sampling. Like if I'm gonna use a standard here for my simulation and then use hover for the MD, that I don't know if it will be reliable, but this is all I know in this point.
Are you satisfied? Or it creates more questions?
I think I have more questions.
Would you like to ask right now? Or would you like me to comment before you ask next question? Okay, so for productive part of our calculations, we are doing what Sarah is showing as NVE, where so NVE is constant number of particles, constant volume, and constant energy. So when we it's microcanonical ensemble, when there is no exchange of particles, there is no exchange of energy, there is no like thermodynamical squeezing of your water piston. And here there is no ambiguity in this table. So our calculations later on are based on molecular dynamics, which with constant energy, microcanonical ensemble. The NVT that has this several thermostats, several options, and probably what Hadassah is asked about, ambiguity about how to, which thermostat is used. It is not the productive part of our calculation, but it is a way how we communicate kinetic energy to all ions, and which point in a phase space we choose as initial step of our trajectory. Sarah, may I ask you to go 2 slides back?
Back.
With the questions, not forward, but back. Slide number 2. So the productive part that generates trajectory is based on last line, Newton's equation, which needs initial values of positions and initial values of momentum. If our geometry is optimized, we have no initial momentum and we have 0 forces. So if we immediately start molecular dynamics or microcanonical ensemble with initial geometries, we will see no dynamics. So we need to remove the system from the equilibrium. And approximately, this is done by NVT calculations, and approximately, or maybe even exactly, it is reproduced by the first line. So one selects T Ri over dt, the velocities of each ion, in a such way so that upon averaging over all kinetic energies, we will get temperature of our desire. So we select a temperature and then do such procedure which will simultaneously assign certain velocities or certain momentum to each ion in such range that it will reproduce the required temperature. Make sense? And this procedure of assigning certain velocities is not trivial. So it is called thermostat model, because there are several ways how to do it. There are some ambiguities, and assigning only kinetic energy is not sufficient. We also need to remove the coordinates from the minimum of the potential energy surface. Therefore, the NVT ensemble, or what we call heating, is performed for several steps. And it is what Sarah was showing as temperature fluctuates and then comes to saturation. So we need to wait a little until our model is approximately in the thermal equilibrium. And then after it comes to the thermal equilibrium, we can remove our path from a stove and put it in thermos, avoid any interaction with the environment, and just look how it moves on its own. And then this motion on its own, MBE ensemble, microcanonical ensemble, serves as an input for non-adiabatic couplings calculation. If one would try to make an experiment to compute couplings based on MVT ensemble, the couplings will be even more discontinuous, because at a time when there are kicks, when the velocities of each ions are randomly changed, there will be big discontinuity in the couplings. Later we will go over and try to compute it. So we need to continue the trajectory without interaction with environment to have more realistic, more mathematically continuous function in the couplings. Does it have more questions or removes their, reduces their number?
Or this is the third.
Okay. More questions to Sarah? So please review her presentation, review the links to templates for the in-car files, create separate directories for heating and thermodynamics, and try to run your model with these settings. Any questions to Sarah? Any questions from Sarah to herself or to her talk?
Professor, I just updated a little bit in the slides, so if I can share with you and you update the link. Is that possible?
Yes.
Okay. Okay, thank you.
Are you going to do it now or at a separate time?
I can share it with you and then in the email and you do
At
it.
the end of the meeting, after we're done with the program.
Yeah.
Okay. So please join me in thanking Sarah once again. So we are coming to glorious completion. We have two more, no, three more. But August, I believe Sarah partially took your piece of bread and showed an example of spaghetti float, but she didn't call it this way, and you can still show your slides and explain a little bit more about the value, how much we all need spaghetti.
Yeah, so for my presentation particularly, it is, yeah, so Sarah covered the most of it, or the main brunt of it, but I'll still share my slides here, just so then everybody can know how to sort of, run ProScript, as well as sort of visualize whatever we get out of a GNU plot. So, particularly what I had focused on was Kuncham orbital energy versus simulation time as the particular spaghetti plot that I sort of plotted. But this can work for almost any spaghetti plot that you decide to go for, whether it be band energy versus time, which is a sort of separate script, but it's the same sort of concept, or at least the same concept in running. So firstly, we have to start with some preliminary steps. So you have to start by running a molecular dynamics simulation, which Sarah had already talked about in her wonderful presentation. And once we finish our molecular dynamics simulation, we can visualize simulation data in many different ways. So one of the ways that we've previously done in Dr. Keelan's class was temperature versus time. There are movies that we can do, which Sarah touched on. And I had previously touched on band energy fluctuations, just like briefly mentioned it. But particularly just for today's, we're concerned with Kuncham orbital energy fluctuations, which Sarah had already shown a figure of. So this is just a brief step-by-step. If you follow all these steps, you'll get out whatever graph that you want. So firstly, again, we run our molecular dynamics simulation. And then once we're done, we call the energy extraction ProScript. And so this is just Perl ~bin/ state _ energy _ extractor.pl. And then you do space, the orbital increment below HOMO that you want to look at, and then space the orbital increment above the LUMO that you want to look at. So let's say like your HOMO is at index 200. If you input 160, space 240, you would end up plotting the energies for the HOMO minus 40 through LUMO plus 39. And in this case, you typically want to do plots probably in the HOMO minus 20 to LUMO plus 20 range. Anything more than that, and usually the spaghetti plots get a little bit too dense and a little bit too hard to read. And so usually you just want to do a total increment of 40 separate orbitals where the HOMO is the center one. And so for your third step, you want to rename your output of Perl script to B. So this is because the script that we use for GNU plot will only read it if you rename it to B. So we do copy energy underscore by underscore band to B. And so then your script or sort of your output is renamed to B.
Okay.
And then,
Interrupt in the middle and add a comment because I saw that someone was smiling and laughing about this name of the file. So it doesn't necessarily needs to be it can be A or C.
Yeah.
Script, the next script, GNU plot fluctuations, does literally names the file name again and again, like 40 plus 40, 80 times, telling like take this file and plot column number 70. And if the name of the file would be long, the script itself will be longer. So it just shorter name. So nothing specific with line B or letter B.
Yeah.
Okay.
Yeah. Mm-hmm. Yep, that's a good aside. Thank you. I appreciate that. And then just for step 4, just sort of your final step is that you visualize with GNU plot. And so what you do is disregard the capitals here, otherwise you'll get an error. So don't actually capitalize the G in GNU plot and don't capitalize the P in PS2 PDF, or else you'll get errors. But you do GNU plot /bin/GNU prog underscore fluctuations, and then you'll get a output file called fluctuations.ps. And then what we want to do is we want to take that PS file and turn it into PDF so then we can visualize it. And so we do PS to PDF space fluctuations.ps, and that'll turn it into fluctuations.pdf. And so this is generally what that'll look like. So on the left is just sort of an example of running through molecular dynamic simulation and just doing this exact thing. So I have highlighted the specific commands that are shown. And one thing that is pretty important is that you cannot, you can't really open the PDF inside of NERSC itself. And so what you have to do is you actually have to transfer it either to your own computer or to a separate server like Photon, and then transfer it to your own computer using WinSCP. And so in this case, I had SCP'd the file over to Killen's Photon. And then from there, I took it from the Photon using WinSCP to my own computer, and then you can visualize it, which this is Aaron Ford's old plot. And essentially what this will show is your energy fluctuations or your orbital energy fluctuations with respect to time. And so then when you're doing your simulation, you can visualize how your electronic structure is actually changing based off of orbital energy. And so this can indicate a lot of things. And so it's useful to also have a movie along with this sort of plot. So then we can see, oh yeah, you know, this is why the electronic structure changed here. Or if you get a big change, you can maybe see a large structural difference. So, okay. That is my presentation.
Please keep the image on. Please join me in thanking. Okay. So any questions? Practical or philosophical? So I would be very, let me do strange thing and ask a question about August's presentation to Adam, just because their names start with the same letter.
Yep.
How do you interpret this figure? What can you learn? What does it tell us? Just philosophically.
It looks like the different colored lines represent
different colored lines.
Well, they represent different orbitals.
Yeah.
Correct.
Yes.
I guess the ones of interest, but it represents how their energy changes over time, which is relevant to like things like charge transfer.
Okay.
Yeah.
So if I would redo this figure with 0K temperature, how this image would look like?
It would really just be a flat line.
Yes. And if I redo it with 600 Kelvin, how would this change?
It would be a very non-flat line.
Okay. And right now we do see that, let's say, let's look on the orange line. It looks like a little dirty oscillations. So it's not a pure harmonic oscillation, but it goes up and down, and one can say it does it 1, 2, 3, 4, about 4 or 5 times during this trajectory.
Yeah.
So like a period of 200 femtoseconds. So if we increase the temperature, what would change? The period, amplitude, both or none?
It's hard to say. I'm not sure, but I would guess amplitude would be notably different.
Okay, yes. And it is expected that frequency is not going to change much because it is related to eigenfrequencies of nuclear motion and whatever you, unless the bonds are broken, it will be the same frequency. Okay, so the higher the temperature, the bigger amplitude of these oscillations. And in some sense, this figure illustrates a response of electronic degrees of freedom to perturbation to nuclear degree, to thermal heating. I don't know how to formulate another questions to this. August, do you have any comments or feedback to this little discussion between August and me?
Honestly, like everything sounded fantastic. Adam got, mostly all my thoughts out. So I think you did great. Yeah. As for any extra sort of like comments, I guess, I just want to reiterate that this will mostly work for any proscript that you run regarding GNU plot. And so like we had sort of like seen with like Sarah's, it is a very, very similar process. So with respect to the code, at least, just you can always look back at this if you need like a little bit of help with like one of the scripts. It is nearly 100% the same process most of the time. So.
Thank you. I noticed you really wanted to ask a question or comment.
Yeah, in that plot up there, I noticed that there's a big gap of nothing between -4 and -3. Why is that?
That's because that corresponds to the band gap. And so when you have a HOMO and LUMO, they can sometimes form a band gap in some structures. And so this band gap is correlated to the KSO energy of the HOMO, which is the bottom one. So that one will be less energy, and then the LUMO would be the top one. And so that one's the orange sort of figure. And so that just means that if you excite an electron from your HOMO, it would take like a lot of energy to get up to that LUMO. That's sort of what that means.
Okay, thank you.
Yeah, no problem.
Hadassah, any questions? August, are you going to do the same figure for silicon cluster?
That's the plan. So next week, when we have to, or sort of over this week, I guess, and also partially Monday next week. But yeah.
In addition to presentation next week, for small silicon cluster, it will be like 1.5 hours total for heating molecular dynamics in this image. So just share with your advisor and CC to me if you want to, but just try. It's not required, but it's for your own benefit.
Yeah. No, absolutely. That was already my plan. And so right now, I've already completed the geometry optimization. So I'm just about to do the heating, and then which I'll do tomorrow. And then the molecular dynamics will probably come either later tomorrow or the day after. So we'll see what happens.
You're extending the pleasure.
Yeah. Thank you so much. I appreciate it.
More questions to August? 1, 2, 3. Let's thank August once again. So we have 2 more Peyman. August, please stop sharing.
We are continuing the food science presentations. Peyman, would you like to share a screen and teach us about broccoli? I think that the name of broccoli plot came from John Fogel, who was a really student in this group like 5 years ago, and now he's a staff member of San Diego National Lab. Okay, so, and your microphone may have been muted. Please unmute your microphone.
So I guess everyone can hear me, right?
Yes.
So hello, everyone. Today I'm going to talk about the tracking trajectory of atoms in Jmol, which could be kind of beneficial because in some project, especially in my case, the case that I'm working on right now, which is about the carbonation and hydration of calcium silicates, could bring some insight for the audience. So these kind of tracking trajectories are called broccoli plots that I had no idea before Dr. Killing told me about. So broccoli plot is the visualization of trajectories of atoms after calculation and molecular dynamic simulation. So for plotting such figures, we need the Jmol software, obviously, and also the Java must be installed on your PC. So as two previous fantastic speakers talk about how to get the movie from the VASP, we need to use the actually command in the directory of the query to get the XYZ file. And after that, we just upload that file in the Jmol. And by just actually following this simple procedure, we can actually see all the trajectories of all atoms. So you just need to choose the Tools tab, Animation, and just click on the All Frames tab. So here is just an example from titanium hydroxide that I first optimized. I performed the geometry optimization for the ground state, and then just following the mentioned procedure, you can actually plot the all trajectories of all the atoms. And the second example is actually the project that I'm working on is the carbonation of the calcium silicate. That first I optimized the crystal of the calcium silicate in the presence of the water molecules and carbon dioxide molecules. And in the second figure, you can see the change of trajectories of all atoms. So yeah, that's my presentation. So please let me know if you have any questions.
Okay, please share with me. So any questions with the value of this little skill to your projects? So let me add a comment.
I have one.
Go ahead.
Yeah, so do you plan on, and then if so, do you plan on like putting the trajectory in like a 2D plane view? For example, I could see a benefit of saying like how high does one atom go relative to another, and it might be a bit too congested in, you know, like the pictures you've shown. They might be able to show some like 2D graph to show the distance or something. So do you plan on doing that, or do you just expect to keep like this 3D figure that you have now?
That's a really good question. Yeah, thank you for asking that. Actually, it's I don't know if it's kind of professional way to just show the 3D or even 2D plots. So based on when I reviewed, for example, different literature, they do not, they only put some plots or 3D or 2D figures just for for I don't know, just for showing the audience the procedure, the trajectory of different atoms. But if you want to, for example, conclude the scientific statement out of your calculation, you need to show the diffusion plots, which is the change of the XYZ, the coordinates of the atom versus time. These kind of plots, I'm not sure if they, for example, can prove any specific things.
Okay, so just, yeah, are you planning on doing that, or what do you expect?
I prefer to show 2D plots. I've never thought about showing the 2D plots.
Okay, thank you.
Let me add a comment. I don't know how to formulate a question, but if, for example, I start new system that performs some motion that is not known for me, if I just at the beginning. So one can learn general trends from this type of image as follows. Like lighter atoms are more mobile. They create a blur around their center, like it is shown here. The heavier atoms do not move and stay as a spheres. If we do have absolutely rigid solid, then it will be just little fluctuations of all ions. If you do have diffusion, then diffusing agent will move and leave a trace along the trajectory. And if there is a chemical reaction with bond breaking, then it will be, one would immediately notice that there is much more signals, much more signatures in this broken plot will show only in the range where bond is being formed or broken. So it will be basically trajectory of ion moving from one spot to another one. Where this image was used, this style of image was used by a designer of the name, by John Vogel. He was considering quantum dots with ligands, and he needed to prove how much contribution to nonadiabatic dynamics comes from motion of ligands and from motion of the core ions. Like in your model, there are methyl ligands and there are core ions. And on this broccoli plot, it is very evident that core ions do not move at all, and all motion comes from ligands. So it's not going back to discussion between Meade and Peyman. So this style of image is not quantitative, it's more qualitative when one needs to select direction of thinking and do preliminary analysis. But it saves efforts on, it replaces like 1,000 frames of movie in form of condensed single image. More questions to Peyman? Or any questions from Peyman to himself? One. Questions two. Questions three. Let's thank Peyman once again.
Thank you.
Thank you. And the last but not least, presentation by Meade, which is a very unique direction. It's only 3 slides, but it is very intense. So if you ever consider to compute photoexcited dynamics, be very careful and please speaker with practical questions.
So can I begin?
Okay, please go ahead.
Okay, so hello everyone, my name is Meade Erickson, and in general, I just have like a flow chart that I generated a while ago. I've cut out parts of it, but for the most part, what we're doing is we are taking an electron from one orbital, such as ground state, and putting it into a different orbital, an excited state. And so on the bottom is actually where we would be transitioning orbitals. And what happens is this electronic excitation is able to be calculated, and this change from ground to excited Thus changes the ionic positions as well, and energy gets incorporated into the system. And it kind of, once the ionic positions are calculated, the new one, the next frame, the electrons are then gone to from excited to ground over and over again, and the cycle repeats. So from start to finish, we would see that orbital change, or the positions of the orbital structures change, and then also the atoms themselves move. And so this is kind of simulating UVE radiation by taking an electron from one orbital and putting it into another and repeating this cycle over and over again. So that's that. What I kind of have here is two in-car files, one being in-car ground and one being in-car excited. And what's happening, like I had shown you guys previously, we are calculating like a ground state versus an excited. So the main difference, I'll go over this a little bit more, but the main difference between these two comes in the electron locations. So for example, we have all the electrons are occupied in the first 112 orbitals of this specific system. And then after that, there's 48 unoccupied orbitals, okay? So I believe there must mean there's 160 total orbitals in this specific system. And then on this case, we had taken one from 112, so we took HOMO, or electron, and we inputted it into 116, which is LUMO plus, so 14, 15, 16, so LUMO plus 3, I believe. So HOMO to LUMO plus 3, and so this in-car files are, it's a little snippet is calculated, and then it's transitioned to excited state, and then it's going back. So this reversed cycle is constantly going back and forth between the ground state and excited, but we can kind of go over a little bit of the in-car file. So kind of the main things that that is unique to this kind of setup is the beginning and end temperatures are 0, because the energy that's accumulating within the system is due to the transition of these of the electron. Okay, so I titled those two things. We do need wave and charge car files to get like the orbitals that we had previously mentioned. Wave car, I believe, gives electron density information, and stuff like this is all very important. I feel like for the most part, I highlighted the most important things. Previously, we had mentioned S-mass in a different presentation. In our case, we were saying total free energy is conserved, but kinetic energy is being inputted once again due to the movement of these electrons. But these in-car files, I have not seen them actually on the bin directory, so I will most likely just input these in the bin directory as their titles, in-car ground, in-car excited, unless Dr. Hahn or Dr. Killen are against such a thing, let me know. But I just don't see them present available. I will put them in there for us later, unless otherwise mentioned. And then next little slide. I have a nice demonstration here for you guys, a video in the bottom right corner. We started from, let's say, a ground state, and this occupation, deoccupation of the excited, of these orbitals slowly transitions and degrades the polymer itself due to the high energy, kinetic energy accumulated within the system. So this specific one has been done in a vacuum. We've actually shown that it can be done in aqueous environment as well. So solvents should be able to be used in the future stuff as well. But the debug or like .sh file you'd be using to submit this, you can see how we have like an excited in-car, and we're taking, we're like other situations, we're taking the car and putting into the post-car, and this is happening over kind of a large duration. And so this will happen for, let's say, one frame. Take a little snapshot, then go to this one frame. and then we go here, and then back down, and so once again, that repetitive cycle exists. So the main things that we're seeing is we're able to kind of connect all of these frames into a movie. So all of this specific section is taking the XYZ files and putting them into some sort of movie where we're able to see this excitation process take place. Additionally, there's like TTOL files, which I'm not sure if it was mentioned in this specific presentation, or previous ones today, excuse me, but it kind of gives us total energy of the system and other details. So that's my main presentation. I thought it was important to kind of show you guys, it doesn't need too much input from our debug file. So it doesn't seem to be needing too much computational input, but yet more the better as always. And just letting you guys know. So that's what I have presented. I see a couple questions lined up. Does anyone else, should I start reading the chat, or does anyone else have a question?
Okay, please join me in thanking Meade. So any questions? If anyone is planning to run similar jobs, try to challenge me with questions.
Okay, I can read the chat, but actually, just for clarification for Dr. Hahn and Dr. Killen, are you guys okay if I input this into the bin file, like this debug? I'll name it as like TDESMD SH, and then the in-car excited, in-car ground.
So maybe in near future, given after you finish your content project, you will do this one. So try to ask questions if it is not clear. And your side project can be related to it. If you have questions, just go ahead.
I apologize. I wasn't able to hear you. I don't know. You seemed far away from the mic. I apologize.
So I did type some questions in the chat line, but maybe I'll ask directly. How many times do you switch between ground and excited, and how to control it in your script?
How many times? The ones that I have seen would be hundreds of times. I don't believe I was seen over 1,000, but hundreds of times. And how is it?
It's 100 or like 154. I do see you have a cycle at the first line of your script.
In this particular case, like I said, 100. So, the difference here is 155 from 145 to 300. But in other trajectories, it's been over that even.
Okay, and how long does system live in each of the states, in ground and excited? Like if you go one slide back, how long this molecular dynamics is in excited state is running? What's the interval? Can you go one slide back?
I would say a picosecond.
No.
A femtosecond, sorry, excuse me. I would say a femtosecond, but that's not what I can relate to computationally because we put POTOM as one, so that's femtosecond.
So how many femtoseconds?
I believe one.
No, what is the value?
Okay, hold on. If we have 5 steps with 1 femtosecond each, that's 5 femtoseconds.
Okay, so it's a very quick transition from ground to excited. 5 in each, and then 155 cycles.
Yeah, 5 femtoseconds.
Okay.
Thank you.
Yeah, thank you. And this
that
measure of intensity of laser, it's it corresponds to very intense laser. If laser field is weaker, then it will be less frequent transitions. Can we go one slide forward? One slide forward, next slide. So the main beauty that I cannot believe up to now it's still impresses me that it is possible to use the srun command several times in one script. So in the red, srun command, which means you run VASP and then you run it again and again many times in the same script. So this tool, which is practiced by and explained by Meade right now, will be used by all of us, even if you do not care about bond breaking, for computing couplings. So these scripts that we are going to learn next week will be based on rerunning VASP code several times within the same job scheduling script. So subsequent running of the code again and again in the script. Any questions, suggestions, expression of admiration to the speaker? Everyone is tired. Questions 1, questions 2, questions 3. Let's thank Thank you very much. Your talk is very important. So it's a unique calculation on one hand and a specific skill that will be used by all of us for computing couplings later. So you can stop sharing, and I will briefly share the list. So here is the sign up list that we can yes, and I will just add it into chat one. So if you didn't get it before, so it's better if you can feel volunteers. So Adam, I put you as a volunteer to number 1. So number 4 and 5 from today are just rolled over to next week because it could be useful, especially to those who just started. And then the main idea is to get files named coupling, 1,000 of files by such name in 3 ways: without spin, which will be number 6, with spin polarization, and with spin orbit coupling. And there are about 4 talks in between with which overview the philosophy of this calculation. So the practical way is to go from this fact, from 1,000 of files like this, to 1,000 of files which name this way, and whatever it takes it in between. So please consider to volunteer and type in your names. If more than 1 volunteers are appearing for one subject, is okay. It's better than none for another subject. And if no one volunteers within 2 days, I will just randomly distribute and suggest if you're able to present. Okay, I believe the meeting is done. Many thanks for contributing to discussion, for attending. Special thank you to all presenters. And I believe the meeting is done. So feel free to depart and disconnect. If there is something to discuss, to share some material, to discuss something in person, just stay connected or stay in the room. We'll briefly chat to whoever requests a brief discussion.
For your, like it said, modify the B script. Are you saying like we're going to run a file and the absorption spectrum is going to be automatically generated, or what are you kind of wanting us to present how to get absorption spectrum, for example?
Okay, so absorption spectrum is a basic skill that everyone in the course practiced in the middle of the course, but we do have a couple of summer interns who just start this activity, and it's better if computation of spectra is given an overview. So David, provided an overview of spectra with speed orbit coupling, but I doubt that those who just start will immediately jump to it. So it's better to start from simpler version. So it's those are simple things, and I am suggesting to start our next meeting from absorption spectra is as follows: the Fortran script that computes overlap, that computes non-adiabatic coupling, and will be called inside the V script, is nothing but modified Fortran code for absorption spectrum. So from the point of view of programming, spectrum and non-adiabatic couplings are computed in the same way. So overviewing details of how to operate absorption spectrum code immediately brings us to practical steps to compute non-adiabatic coupling. So it will be arrangement. Yeah, thank you for asking, and I think our discussion brings more logic to this series of meetings.
All right, thank you for clarifying. Thanks.
Peyman, do we need to discuss anything right now, or we can continue by email?
We have time if you want to discuss anything more about. You want to discuss about internship?
If we have some one-to-one discussion, we can do it by email because there are several people in the room.
Yeah, sure, no problem, no problem.
Okay. Okay, yeah, thank you. August, do we have to discuss anything?
Yes, yeah. So just so you know, I won't be able to join for next week's meeting because I have surgery that day. And so we will have to continue the discussion some other way. So here's what I'm thinking. So obviously I'll send you any data I get from the molecular dynamics simulation. If you want anything further, just send me an email. And if you want, I can maybe try to make like a recording of something, you know, we'll see. But if you need anything, just let me know. I'm probably going to be out for a day or two, just recovering. But besides that, I will be active on email. So just let me know if there's anything I can do. So.
Okay, great, great. I don't know what are the right words, but good luck with surgery. Have it successful, painless, quick.
Oh yes, thank you. It's just a wisdom teeth surgery, so I have to get them out, and it's going to take me a day or two to recover. But besides that, it should go well. So yes, I'll hopefully see you tomorrow and the next couple of days. But then Tuesday I'll be gone. So, but we can still discuss during that time. So
okay, very good.
Okay, gotcha. Thank you so much.
Thank you.